Good morning, everyone. This is Mark Richardson speaking from Vibrant Technology in Scotts Valley, California. It's 9 o'clock on Wednesday morning here. Beautiful sunny morning, so welcome to all of you, wherever you may be listening in. Today we're going to cover FEA Model Updating, and that is a capability that's built into the experimental FEA option of EMA Scope. So I'm going to take you through a number of commands that are part of this option, and we're going to look at two different cases. The first one is the tutorial number 15 in the help and operating manual. So if you open up your tutorial help on your system, if you have EMA Scope, and you look down here under the tutorials, there's 15 of them. And the final one is called FEA Model Updating. So we're going to use the many of the commands from this tutorial, and I'll take you through them, and we will look at how we update the thickness of the vertical plate on the Jim beam so that the FEA mode shapes, the frequency of those mode shapes, more closely match the experimental frequencies that we obtain from an experimental test of the Jim beam. So let's go ahead and open that project. Mine is located under Documents, EMA Scope VES, Tutorials, and then Tutorials. So if you've installed this tutorial VTPRJ, this project, on your system, you should be able to find this same project. So I'm going to double click on it right here in the start page of EMA Scope, and I'll open that up right now, and you can see here's a model of the Jim beam. So the Jim beam, this is a photo model. It's got 3 different aluminum plates that are anodized in different colors, and they're attached together with some cap screws. You can see the 3 cap screws here on the top. So this is what we call an experimental model, or a 3D model, and we tested this with an impact hammer, and now I've turned on the numbering of the test points so that even though this model has additional points in it, the only ones that are numbered are, in fact, the test points. So we impacted it with a hammer, and this was a roving accelerometer test where we roved a triaxial accelerometer and we impacted the Jim beam at point 15 in the vertical direction. So out here on the end of the upper plate, we impacted with a instrumented hammer, the hammer that measured the force with a load cell, and we roved a triaxial accelerometer around all these different points. Each time we impacted the structure, we would measure 3 frequency response functions, or FRFs, and then those have been curve fit. And over here on the right are what we call the EMA shapes, or the experimental mode shapes. You can see there's 10 of them in this list here. This is a spreadsheet of the frequencies and the damping values. Most of you, if you've used EMA Scope, are very familiar with the Jim beam structure. We use it for a lot of different examples in EMA Scope. Down below here are some FEA modes, and we'll look at those in a minute. These were calculated using tutorial number 14 in the help and manual. Let's go back and look at that for a minute. So here is the help. Let me make this large, and we'll just go over here and look at tutorial 14. This is called experimental finite element analysis. Now that may sound to you like an oxymoron. Finite element analysis is just a computer model. It has nothing to do with the experiment. We have labeled our version of finite element analysis in EMA Scope the finite element solver and the ability to put elements on a 3D model as experimental finite element analysis, and that's to denote the fact that we can take this same model here that we use for experiment and looking at experimental shapes, and we can create a finite element model from it. So that was done in tutorial number 14 in the manual. Let me bring up let me just start the animation here and we'll do a comparison animation. So I'm going to do compare shapes, and now we're looking at the two models. I'm going to turn off the point so they'll animate a little better. On the left, of course, is our experimental 3D model being animated with our experimental mode shapes, or what we call EMA mode shapes. On the right is the finite element model that was built from the Jim Beam experimental model, very simple one, with plate elements in it. Now you can see that there are more points. If I turn off the surfaces, you can see the various points. So the model on the left is animating with 30 experimental points, and then we're using our interpolation to interpolate the points right below each experimental point on those plates. On the right is the FEA model that we built from the experimental model, and it's being animated with the mode shapes down here called the FEA modes in this shape table. So I have the two shape tables here on the right and the two models animating with the data, the different shape data. Now, in a comparison display, we can display the modal assurance criterion, and I do that by turning that on in the structures options box. It says right here, show MAC. So we're going to show the modal assurance criterion value, and that is a numerical measure of how much alike these two mode shapes are. Now they look different the way they're animating here, but the MAC value is 96%. So if I put this down here at the bottom, you can perhaps see it a little better. I just dragged it down to the bottom, 96%. So that's basically saying anything above 90% is saying that the two mode shapes are the same. Now let me click on this next experimental mode, and you can see that both mode shapes changed. And again, the MAC value is 96%. Well, how did that happen? I have another command turned on in the Animate menu. If I go down here under Compare Shapes, you can see that I've got maximum MAC enabled or turned on. What that is going to do in a comparison animation, when I'm comparing, it's going to find the pair of mode shapes that have the highest MAC value and animate them together. So that's what we're looking at here. So as I click down through the experimental shapes, you can see that it's choosing a different analytical shape, and again, 95% likeness. Let me just click all the way down, and you can see that there is an analytical shape that matches up with the experimental or the EMA shape. So I'm clicking down here in this shape table, and it's finding the matching shape. Now I can also click down here in the FEA shape table, and it will do the same thing. It's going to now find the experimental mode shape that matches up. And when I say it matches up, it's got the highest MAC value among all the different mode shapes. But you can see that there's some other mode shapes in here, especially in the FEA model. Let me click on this one, zero frequency. Now that is what we call a rigid body mode shape, and the MAC value is very low because there is no experimental data to match up with that rigid body mode. Typically, we don't measure the rigid body motions because the frequencies are zero in this case, and number 6 here is at 2 hertz. That's still a very small value. Let me enlarge this a little bit so we can see that. I held down the control key and spun the mouse to enlarge the spreadsheet. I can do that with any of the spreadsheets. And even this mode here, which is the first bending mode of the structure, we don't have a mode shape that matches. You can see the one that comes closest is at 460 hertz, and that's certainly a different mode shape, and the Mac value is very low. Now, what else is going on here? How come these things don't match up a little better? Let me go back and click on the first mode, the experimental mode, and you can see that even though the Mac value, now I'm going to drag this scroll bar and I'm going to overlay the two mode shapes. And they just don't match up. You can see there's some phase in there. Now that's because the experimental data has some phase in it that the analytical data does not have. The way I can resolve that issue is under the Animate menu. There's a command called Normalize the Shapes. So I'm going to turn that on. Now you can see that the phase has been removed so that the complex mode shape on the left matches the normal mode shape on the right, but they're still out of phase. So I need to do one more thing, and I've added a button up here. This is a command. I've added it to the toolbar, and you can do that by customizing your toolbar. I've added a command called Animate Compare Shapes Flip the Right Sign. Now what that means is I'm going to flip the sign of the FEA, or the analytical mode shape, so that maybe it will match up with, and there it is. I press that button and you can see it's flipped the sign and they lay right on top of one another. Now the Mac value has told us that they're 97% alike, so you can see from the animation that basically the FEA model lines up perfectly with the EMA mode shape. So let's click through here. Oh, and there's a phase, so I need to go back here and unflip the phase, and there they line up again. So as I click through the experimental shapes, in order to get them to coincide, I need to flip signs back and forth. But again, the Mac value is telling us that they are in fact the same mode shape, or very close to one another. So this is a confirmation between experiment and analysis that in fact the analytical modes that we got from a very simple finite element model of this structure match up very well with the experimental data. However, if you look at the frequencies here, you can look at this first mode I clicked on, 165 hertz. Let me make this a little larger so we can see. 165 for the experimental and some damping. Down here the analytical is only 143, and of course no damping. We didn't include damping in the analytical model. That's just too difficult to do in most cases. If I click here, 224 for the experimental shape, let me change the phase again so the shapes are the same, but the frequencies are quite different. Only 203 hertz. And then as we go down here, we can see that even though the shapes are lining up one for one, the frequencies of the FEA shapes are all less than the frequencies that we obtained from experiment. Now there can be a lot of reasons for that, but FEA model updating works on the premise that the experimental frequencies are more accurate, and that we've made some assumption in the FEA model that isn't quite the same as the physical world. So let's go look at model updating, and what we're going to do here with the FEA model updating, in this case, again, this is the tutorial, is we're going to change, we're going to allow the the thickness of the vertical plate here, the plate in the back. Remember, these are plate elements here on the finite element model. We're going to change the thickness of the vertical plate and ask FEA Model Updating, what thickness can we choose that will make the frequencies match up a little more closely. So let me stop the animation here, and we're going to go up here under FEA. So when I'm in the structure window, my menus will show all the commands available for the structure, and down here under the FEA menu is FEA Model Updating. So I'm going to click on that, but this is not the window that I want to use. Let me change that and open the FEA model, because I want to do the model, I want to do the updating on the FEA model, not the experimental model. So now I'm going to, and you can see that over here it's a connected source of mode shapes are the FEA modes. Those are the ones we were looking at with the comparison animation. Let me go back here and open up the FEA Model Updating. Now it's saying the following FEA objects will be used, 16 FEA quads. So what has happened here? Let's cancel out of here and look at what that means. If I go to FEA quads, which are the elements that were used in this model, there are actually, and I've selected them as my current drawing object, or in this case FEA object, you can see that most of the quads are hidden. They're not visible. Only 16 of them are visible, and you can see down here that there are different numbers in the spreadsheet, but those are the ones that are the 16 that correspond to the vertical plate. I'm going to select them, and then you can see that those are the plates elements for the vertical plate. All the other elements are hidden. So that is the way that FEA Model Updating works, where I can have lots of elements, but I only want to update certain ones. And so let's go back and open up the Model Updating, and it says down here, reminder, hide all the FEA objects not intended for use. So we're going to go ahead. Now I get a dialog that says, tell me which FEA shapes you want to use and which EMA shapes. Again, we're going to compare frequencies of the EMA shapes with the frequencies of the FEA and update the thickness of the vertical plate in order to make them line up better. Okay, now it's telling me, warning, some of your shapes are selected. Remember in EMA Scope, if I select things, then it only works with the selected shapes, and if I unselect everything, then it will use all the shapes. So I want to use them all. So it says, do you want to unselect? Yes. Now it's saying the same thing for the EMA shapes, and that's because we were animating out of those shape tables, and we were just comparing one shape in one table with one shape in the other. So the animation ran off of the selected shape also. Okay, so here we are, and let me make this a little larger. Again, I'm going to hold down the control key and spin the mouse wheel so that you can see these two spreadsheets. So this is the model updating. Let's look at the top spreadsheet first. So I'm going to drag this way down here. What you're seeing in the first column here are the frequencies of the FEA shapes. These are the rigid body modes, the first 6 of them. Then we start into the flexible modes, and we had solved for 20 modes. In the second column are the EMA shapes that we got from curve fitting some FRFs. Now here, the software is automatically trying to match up modes based on their MAC values. So the same thing that we looked at in animation, but you can see that these rigid body modes have very small MAC values. They don't line up very well with any of the analytical modes, or the experimental don't match up with the analytical. But if we get down here to 143, now you can see that the software has matched up the 165 mode, the EMA mode, and right on down through number 17. And then again down here with the FEA mode, 18, 19, and 20, they don't match up very well with any of the experimental data because we don't have any experimental data there. Again, the MAC values are low. What we're going to do then is choose, let's just choose one of these modes. Let's choose that for our error function. And that's going to order all the solutions that we find according to the difference between the solution frequency and what's called the target frequency here. So these are just some numbers. I can paste any number I like in there. And I can also, in my error function, include the MAC value of the mode shapes. But here we're just going to match up frequencies to start with. Now let's look down here at how we set up the solution space in this lower spreadsheet. Here are all the physical properties of the aluminum plate elements that I can modify in order to make the frequencies match up more closely. The current value of the FEA model is 0.375 or 3/8 of an inch. You can see the units here. Again, us Americans, we use the obsolete British system of units, inches and pounds of force and pounds of mass. You can set them up in metric and it will make more sense to you. We're going to just select this plate thickness as the property that we want to vary. And over here, we're going to vary it from a minimum value of 0.3 to a maximum value of 0.6. So the software will look at the current value and pick numbers that surround the current value. But again, I can go in, these are spreadsheets with numbers. I can edit those numbers to be anything I want. Over here, I've told it to take 50 steps. So what that means, it's going to solve 50 different model updating cases between 0.3 and 0.6 inches. And then it's going to order them according to whichever solution minimizes the difference between the solution frequency and the target frequency. So that's FEA model updating. Now what's going to run in the background is our SDM algorithm. For model updating, it's a little bit different than the standard use of SDM. SDM normally is a way of modifying a structure by adding things to it, adding stiffeners, adding mass, adding dampers, adding tuned absorbers, or removing them. Remove stiffness, remove mass, and so forth. Model updating is a little different in that we have a model that already has plates that are 3/8 of an inch thick. We need to remove that element from the model and add in a new element that has a different thickness to it. So it works a little differently, and yet it uses the SDM algorithm, which runs very quickly, and will find the new modal frequencies and mode shapes for the finite element model. SDM uses mode shapes of the unmodified. So here, think of this set of frequencies here as the unmodified structure. It's going to go in and do a modification to the thickness of the vertical plate and calculate new mode shapes for the modified structure. So how do I do that? Well, I come up here and there's a couple of commands here on the toolbar, and these are also in the menu up here. Calculate, calculate and order solutions. That's the one I want to use because I want to order them according to the percent difference or the minimum difference between these two values. So I'm going to go ahead and, not these two values, but the solution and the target. I'll go ahead and say go. All right, it's going to say, you can see that my solution space here, if I select all these different properties, I've got these multiplied together. So I get a huge number of solutions. That may be what you want to explore, but it's better to explore just a few of them as a start. And I'm going to let it go. You can see the different solutions going in here, and it's finished already. And it's come up with the top one being, when I mean the top one, you can see I have a scroll bar over here on the side. And as I scroll through, it's changing not only the frequencies and the MAC values of my different modes, but it's changing the thickness of the plate. So I've got 50 solutions here that SDM cranked out, and they're ordered from the best to the worst. Now I'm just looking at spreadsheet numbers here, which is a little hard to see. So we'll look at the graphics. If I push this all the way to the top, that is showing me the best solution in the sense that it minimized the difference between the solution frequency and the target. So I can see when I push this up to the top that in fact it has found a solution. If I increase the thickness to 428, the frequency of that mode is 165. So this is the FEA mode shapes now, the frequencies of those mode shapes, that in this case, because I only wanted to match one mode, it's found it perfectly. Now let me go and look at this solution graphically, and here's what it looks like. Now I clicked on display bar charts. So here we have a number of bar charts. The first one is the percent difference of frequency. So if I just put my mouse down here, I can see that the rigid body modes, the first 6, 100% error between the updated and the unmodified. You can see that the frequencies and the target frequency in each case was one with a minimum, with a maximum MAC, but not a very good number. The 7th mode was that bending mode in the analytical model that had no matching experimental mode. So here's the one that right here is the one that 143 and 165, the FEA versus the target, and that was a 12% difference between the FEA and the target. And here it is after the modification. The percent difference is 0.03, and the frequencies are right on. And if I go along here, I can see that all of the experimental modes matched up quite well with the analytical modes. And remember, these three out here, 18, 19, and 20, were analytical modes that had no experimental counterpart. So those are very high frequencies, or very high errors, 400% and 500% errors, because there was no corresponding experimental frequency. Over here are the MAC values. You can see that the mode shapes were not changed by this change in the thickness of the vertical plate. You can see the MAC values are pretty much the same, the before and after. So the blue is the before and the red is the after value of the MAC. So the before is the FEA versus solution or target, and the after is the FEA modified versus the target. Down here is the solution 429, and it was originally 0.37. So that's the thickness. It's changed. Now, as I pull this scroll bar, you can see all the different solutions popping up, and the errors are changing. So this is an exhaustive search method that tried all of those different, and you can see now when I get down to some of these very poor solutions that now the mode shapes don't match up very well anymore, even though the frequencies are not so bad. So this graphics allows me to pick out, I may not want to pick just the optimum solution, which is this one. I may want to pick one of these other ones because it's physically easier to modify the real structure. And any one of these solutions is still quite good. Now let me go back and show you what we need to change here in order to get that 500% error out of there. Let's just take these three frequencies, which are the modified ones, and let's paste them in here for the target. So I've selected those three cells in a spreadsheet. Now I'm going to select these three, and I'm going to do Control V on my keyboard and paste those in as the target. I'll do the same thing up here for the rigid bodies all the way down through mode number 7, because I had no experimental data to match up correctly with those. But I'm going to say, you know, I want the targets to be what I already know the answer to be here. And now we'll just run this thing again, and we'll get a better looking result that graphically will show us the true difference between the. Okay, so the answer came out the same. I got 4289 after running through those 50 cases. And if I go back to the graphics, let's see what it looks like this time. Okay, well, we still got the 100% difference between the rigid body modes and the experimental, because we didn't have mode shapes to match up for those rigid body modes. So we still got huge errors there. But these errors are much smaller because they matched up between the target and the FEA much better. But over here now we can look at these. There's the 6% on number 7. Let's go to number 8. That's the one we tried to match, and now I can see that I went from almost a 13% error in that frequency down to essentially 0. And all these other ones match up quite well. So I still have the solution down here, and if I drag the scroll bar, I can see that I still have some huge changes. Now as I get up to some of these worse solutions, you can see that the MAC values of the mode shapes are starting to change. And then we get way down here to the bottom, and the MAC values are quite different between some of the modes that I'm really interested in. So those are not good modifications to the FEA model. Let's go back. And so now if I want to look at the actual mode shapes with this modification or this update to the stiffness, I can go up here under solution, and it says save updated FEA properties. So I'm going to go ahead and execute that. And it says property values have been saved for solution 1. I can save as many as I like. These property values get saved where? Well, let's go see where they get saved. I'm going to close out the FEA Model Updating. Properties are under FEA, either materials or properties. In this case, I'm going to go to plates, and there is the updated thickness right there. Here is the current thickness, here's the updated thickness, and this is my plate element. If I go to the, let me close that. If I go to the materials, you can see that none of these updated values. We didn't really change those, so those values for aluminum are the same as the unmodified or the current values. Now we could go back and try those too, but I'm going to move on to another example where we will change some of the aluminum properties. So how do we get the new mode shapes? Come down here, it says calculate updated FEA modes, and I'm going to use the now this is again running through the model updating, so I'm going to use the unmodified and together with the modifications. So that's exactly, here it's telling me again it's going to update the thickness of the FEA quads, and it says it's been completed. Let's put them into a new file called updated FEA modes. Let me spell that, FEA modes. And there they are. And now you can see that the first mode here, the 8th mode is 165 Hertz. And let's just go ahead and start the animation, animate shapes with the FEA model. And there it is. I'm going to click the arrange button up here for animation. And my updated FEA modes are right down here in the middle. So these are the shapes. They haven't been changed. We saw the MAC values were very similar for the modification, but now these are the modes of the updated FEA model that will match the experimental shapes. Now the other thing we can do is just look at all the MAC values. Let me stop this animation. And let's just go up here to the experimental shapes and say display the MAC values. And I want to compare those, the updated FEA modes with, and it says you want to unselect, I say yes. So here they are. Let's just make this a little larger. Here are the MAC values of the updated with the original experimental mode shapes. You can see that most of them are up in the 90%, which is a good correlation. The worst case here is 84%. That's borderline. Anything over 90% is a good correlation between two shapes. Anything less than that, they're starting to vary a little bit. So 8 out of the 10 are above 90, and then we have 2 here that are borderline correlation. So that's all of the experimental, the 10 experimental matched up with the 20 FEA mode shapes. All right, I'm going to move on to the second example, and that is going to be, we'll go ahead and not modify thickness. We've got some solid or brick elements in this second case. So I want to close this, and we'll modify the material properties of the aluminum. Do I want to save it? No. Okay, I'm going to open this one called aluminum plate. Incidentally, we're going to make these 2 projects available with a, I believe, Brian, we're going to send an email to all the attendees. Is that possible? And give them a link to download these 2 projects from our website. We couldn't attach them because the GoToMeeting won't allow us to attach zip files or VTPRJs, only text files and doc files. So we can't add them to your attendance today, but we will give you a link. Anyway, let's go on, and I've added a picture here of the experimental setup for this aluminum plate. You can see the plate here in the picture, but I took a picture of it. So this is an aluminum plate we have here at Vibrant, and we just set it on some foam rubber. and impacted it with a hammer, an instrumented hammer with a load cell that measures the force input. And then over here on the upper corner here is a triaxial accelerometer, just one that we happen to have. A single axis or uni-axis would be sufficient, but we simply used a tri-axis and used a 4-channel analyzer here. So the first channel has the force going in, and then the other 3 channels have the X, Y, and Z, or the vertical, horizontal, axial of the triaxial accelerometer. This is the type of test you can do in, I did it in less than a half an hour, just impacting at 30 different points. You can see them kind of numbered here a little bit. So there's 5 of them down this side and 6 of them down this side. So there's 30 points, 5 by 6 grid. This is another example in your tutorial where we build the flat plate model and animate the data directly. Anyway, let's go back here and look at this plate model. Here, let's go look at the measurements first. We're not going to go through the curve fitting, but just a quick look at the measurements. And I'm going to center this. Here's the 30 measurements, and you can see the curve fit. We just did a quick fit, and you can see that the red line, which is the fit function, lays right on the data. And there's a little bit of noise. Again, there was no averaging, just impacted. This type of a structure is the easiest in the whole world to test. You can see a couple of closely coupled modes here. Because of the light damping, the high Q of these resonances, this type of data is very easy to curve fit and get experimental mode shapes from. So let's animate these mode shapes. Animate the shapes. Now, again, I want to look up here in my EMA model, Z direction only, or 1Z, it says 1Z reference. I believe we're only animating the Z direction, and we'll look at that in a minute. But you can see that it's animating with the undeformed and the deformed together. So these are what you'd expect. First bending mode. First torsion is the lowest frequency. First bending in the long direction, or the, let's say, the less stiff direction, and there's first bending in the stiff direction. There's a second torsion mode or twist. And now as we get up, we get combinations of bending and twist. There's a second bending in the long direction. Second torsion. I don't know what to call that other than a 477 hertz mode. But you can see we found 14 modes, and every point is being animated here. We're not using interpolation. We're animating every point. But this is nice, clean data, experimental data. And there's number 14. All right, well, let's do a comparison animation now between the experimental data and some analytical data. Now, in this case, we built a finite element model using brick elements, and all that's needed there, you do this in one of the commands here. Well, I can't get to it right now, but it's FEA, the FEA assistant. So it's like the drawing assistant. You go in and you grab the a cross-section of the experimental model. In this case, it's not even 2D, it's just a flat plate, and you extrude that cross-section in the FEA, and it creates a finite element model with bricks elements in it. So here you can see, let me go back and start the first. Again, we've got a comparison display. There's the finite element model on the right. the experimental model on the left, and let me just simplify this a little bit here. We'll turn off the undeformed so that I'm going to go here under deformation and turn off the undeformed so it'll animate a little bit better. Now the red dots on the finite element model correspond to the experimental points, and that's another issue that's worth noting at this point. Let me do one more thing. I'm going to make the background, instead of transparent, I'm going to make it solid so you can see the points better. The points on the finite element model that coincide with the experimental test points are numbered the same, and the measurement, what are called measurement axes at each of the finite element points must coincide also with the experimental. So when we're doing experiment, we often can mount accelerometers at different angles. We can impact it with a hammer at different angles. We want to make sure when we compare apples and apples here that the directions of motion of the two mode shapes are the same at each point and that they're numbered the same. That way we can get a MAC value. We can compare the shapes at the common points. Now if they don't match up, if you have a finite element model that was created by the guy down the hall, the PhD FEA expert, and he numbered his node points differently and his axes are differently oriented from your experimental data, then you use what's called model updating or point matching. Sorry, I'm using the wrong terminology here. Let me stop this and show you. In ME Scope, we have a command called point matching. Now, what point matching will do is match up the point numbers between your experimental and your FEA model, and it will also reorient your FEA shapes so they match the orientation of your experimental data. That way you can compare apples and apples. We're not going to go into that today. There's in the tutorial number 15 in your help, we take you through that process of matching up numbers and the measurement axes. Here it's already done because I took my experimental model and built the FEA model from it. So let's go back and start the animation again, comparison animation. And I'll turn the points off. And as I click through, you see again we have a very good correlation between the shapes, the experimental shapes, and the analytical shapes. One model's got many more points in it than the other, and yet the mode shapes are 99% alike at the common points and directions where they match up. So the software takes care of all that for you, provided that you've numbered your points properly on the FEA model. Again, that's why we call it an experimental FEA option, because we want to purposely make the FEA model match up with the experimental model so we can compare answers when we're all done. So you can see of the 14 shapes, it has got almost perfect correlation, 99%, here's 98% between the experimental and the analytical data. All right, let's do some model updating. Again, the same issue. I've got many more modes down here in my experiment or my FEA shapes. You can see I went all the way to 14 here, but the first 6 of my analytical model, again, are the rigid body modes. So they don't match up with very well with any of the experimental shapes. Those are just the rigid bodies modes of the structure in free space. It's a good way to think of it. So there's the first match right there. And again, if I overlay them, I'll have to flip the sign in order to get them to overlay correctly. And there it is. So they're overlaid and very close. Experiment. Let me turn on normalization. That takes the phase out of the experimental data and matches it very nicely with the analytical. So same thing we did with the Jim beam, we can do it here, and we can see that we've got a very good correlation. However, look at the frequencies. Let me make them a little larger over here. I've got 102 hertz here, and down here in the analytical data, the FEA data is 96. And again, 129 matches up with 122. So the frequencies are fairly close. The mode shapes are very close. So let's go do some model updating here of the FEA model to see if we can make things match up more closely. I'm going to stop the animation, and I want to go and start here in the, I'll make this large. I want to start in the FEA model, and I want to do FEA model updating. Okay, so this has 180 FEA brick elements. So the brick elements are between all the different points you can see there where the lines are drawn. We've hidden the points so that only those that match up with the experimental are shown. But there's 180 brick elements, each one being one of these little squares here on the FEA model. I'm going to grab the FEA modes here, FEA shapes over here, and the 14 EMA modes over here, and 1Z was a reference. So that's where we put the triaxo accelerometer. That's why it says 1Z reference there. That was a roving impact test. Okay, again, we had things selected, so we want to unselect both sets. And here we are in model updating again. Now with brick elements, there is no thickness. The thickness of the brick is just a function of the geometry itself. So all we can do is change the properties of the aluminum. We can change elasticity, which is basically a measure of stiffness, how elastic is the aluminum. Poisson's ratio is the best way to describe that is the squeeze effect. If I squeeze the aluminum in one direction, all materials are like a balloon. If I squeeze in one direction, it's going to pop out in a different direction. So you can see 33% means that if I squeeze it an inch in one direction, it's only going to move 1/3 of an inch in the other direction. It'd be pretty hard to do with aluminum, but think of it as made out of rubber. Density, of course, is just how heavy it is. And here we got pounds of mass per cubic inch. So you can see it's fairly light, 1/10 of a pound per cubic inch. Let's change just the density first and see with model updating, maybe the real aluminum of that plate that we tested is not quite 1/10 of a pound per cubic inch. And let's just try again something simple. Let's match up a single frequency here. So what we're going to try to do is get the mode number 7 frequency with this modification to match up with the target frequency, which is the experimental frequency of 101. We're going to do 11 steps. Now this could be any number that I put in here. In this case, let me make this a little larger. You can see it now. Oh, we only got 3 steps here. Let's put in, I don't know, let's put in 15 steps. So let's vary the elasticity or the density. We'll go back and we'll vary both elasticity and density and see what happens. I'm going to put in 15 steps. Let's go ahead and compute. Okay, it says total number of SDM solutions is 15. Do you want to proceed? Yes. Okay, so it's going through with all 180 of those bricks, and it's changing the density. Well, look at here. It actually made it a little bit lighter, 0.09. And let's look up here at the frequency, 101.51. So it matched the frequency up quite well. Now we only tried to match one frequency. We can run this again and match up. You can see the second mode, 129, it's now 128, very close. 208, 213. Let's just say we want to match up the four frequencies as close as possible. So 7, 8, 9, and 10. And let's run this thing again. So we can try lots of different scenarios here, playing the what-if game to see which one is going to match things up better. Okay, well this came up with a little higher value now, and presumably the squared difference between these four solution frequencies and the target is a little closer. Well, you can see that the 101 is now 100, 127, 211, and 242 is right on the money. Let's go look at the, okay, so here are the solutions, and graphically you can see from mode 7 up to mode 20 we have very small errors. These are the rigid bodies that didn't match up very well. And as I drag along here, you can see the density is changing of the aluminum for each of these solutions, and the density did not affect the mode shapes. You can see that I still have very good correlation. Mode shapes did not be changed by the density. But you can see the errors growing over here. If you watch here as I scroll, the errors are growing. So we got some larger errors. You see as I scroll to the top, the errors, the green bars get smaller and smaller. Here, let me, there's some controls here so I can zoom in a little bit. And I'm going to do that. Okay, so here are the modes that I'm interested in, number 7 through 20. Those are the experimental frequencies. Now, as I scroll down here, you can see the errors growing. The green bars are growing. So those are much poorer solutions. And now as I scroll back to the top, the errors get smaller and smaller. And we get all the way to the bottom where we've got some very small errors here. Less than 1% difference between the frequencies of the modified FEA or updated FEA and the target. So we're almost out of time here. I had a lot of other things I wanted to show you, but that basically is, let's go back and run one more case and then we'll quit. And that is, let's let the elasticity vary too. You can see that the elasticity here is 1e to the 7, very stiff. Let's let it vary between 0.9e to the 6 and 1.1e to the 7. And let me compute those solutions. So now we're going to have 165 solutions. And we're trying to match up 4 of the low frequency modes. So this might take us a little time here. We got a lot more solutions to go through. But you can see it starting to vary the elasticity first. And again, this is an exhaustive search. So SDM is going to compute 165 modifications to the FEA model and order them based on the difference between the modified FEA and the target frequencies. So it's still going here at 60% complete. If you can see down here at the bottom of the screen, there's a progress bar that is moving along, calculating all of those different combinations of elasticity and density. And there is the answer. So what this said is that the solution is 1.04 e to the 7, not much of a change. And the density is 0.0966. That is the best answer, matching up the target frequencies with the modified or the updated FEA model. Okay, we're going to conclude with that. Next month, we're going to look at SDM. We're going to use SDM itself, and we're going to look at modal sensitivity, which is a little different, but very similar to FEA model updating. And
I do have a couple questions here too. So.
All right, well, great. We had some questions via email, so let's answer those questions before we quit.
Okay, first question is whether it's possible to use external FEA data from external solvers like Nastran or ANSYS for model updating.
Yes, it is, and I addressed that just briefly where I said that if you don't build the FEA model in ME Scope, you would have to import it into ME Scope from your Nastran or ANSYS files. We can do that. If I go up here and look at the import command, this is where I would do it. Let me go back here under File, Import, and if I go under Structure, and then down here are all the different files that we can import. So here's ANSYS, here's Nastran, and here's STL, UFF. These are all formats where I could bring in my FEA model from the guy down the hall who's the expert, and he built the model. However, you would have to match up your point numbers and your axes, your experimental axes, the FEA axes at each point with your experimental data, which you're not restricted. You want to use axes which are easily mountable when you mount your Excel or when you impact with a hammer, depending on what your roving and your reference are. We didn't go through point matching today, but that's the only other step you'd have to go through in order to match up your Nastran data with your experimental data.
Okay. The next question is, how many elements is it possible to work with experimental FEA?
That's a good question, and we don't have any curves or any specific numbers, and it really is a function of the memory in the computer, the graphics capability. Now, we've animated models in ME Scope with 100,000 node points. I know that some of the FEA codes, Nastran and ANSYS, can handle 1 million nodes. We've never tried that in ME Scope, and that's why we call it experimental FEA. It's a very useful tool for building smaller models. And last month I actually showed you a case where I built a model of a base plate and then a model of a bearing block and attached them together using very stiff springs and SDM. So you can build parts of a machine or a structure very easily in ME Scope, and 100,000 nodes would not be out of reach. Again, if you have the memory in your computer. But then you can attach all the parts together using SDM and using substructuring, what we call substructuring. And all you need are the mode shapes of each of the different parts of the machine or structure, and then SDM will put them all together, and you come up with a set of mode shapes for, FEA mode shapes for a more complex structure. I hope that answered that question.
Okay, and is it possible to work with rods and bars?
Yes, absolutely. I didn't show you all of the types of elements, but rods and bars are, let me just go into the properties here. These are all the types of elements that we can use in the experimental FEA, in the capability of ME scope. So we got masses, springs, dampers. Those are nice and simple. Point masses, springs between 2 points, and then we can have torsional and springs in specific directions. Same with dampers. SDM handles dampers very well. I can even add dampers to my FEA model, and we use the SDM algorithm along with an FEA solver to come up with the damped modes. That's something that's unique to us. Most FEA codes don't deal with damping very easily, at least. Rods, bars, plates, solids. And we have 3 types of solids, bricks and tetrahedron. Gee, Brian, what's the other one? I've forgotten it. But anyway, we got bars here that have, area and inertia terms, and rods that include area and inertia. So we've got pretty much these are standard FEA elements. Dampers, of course, we just have the damping amount. Stiffness, we got the stiffness amount. Plates, we have a thickness along with a material. So we start you out with a few different materials, but you can add your own materials. That comes up here in a different spreadsheet. FEA materials. So we've designed this more for the experimentalist. It doesn't have nearly the sophistication of an FEA code, but for comparing experiment and FEA, or analytical and experimental results, it's very useful and very good. And last month I showed you some shape expansion capability. Maybe next month we'll get into some of that, where we can take the experimental modes that only have a few degrees of freedom and expand them, either mode shapes or ODSs, into shapes that have the number of degrees of freedom of my analytical data, which is typically many more degrees of freedom. So we can do some different things there. Any other questions, Brian?
That's it.
All right, well, thank you all for coming, and we're recording this, so it's going to be out on our YouTube site here in a day or two, so that you can play it back and look at this webinar over again. Thank you all for coming. We'll see you next month, where we will handle SDM and some of the things we can do with that. Talk to you soon. Bye.